So hello everyone, just give me some second. So yeah, I think I'm audible. So okay. So hello everyone. So I'm SRIPAN. I'm working as a PMRF at ITBHU, and this is the 10th week lecture for this particular course of fluid dynamics for astrophysics. So we started with basic hydrodynamics, where we don't include the magnetic field, but from the last lecture in week 9 we introduced magnetic field along with our plasma. So we basically move on to the magnetohydrodynamics regime, and when we are talking about magnetohydrodynamics, we are basically considering the fluid description. And so into this class we will also try to solve some MCQs and or objective type questions one by one, and which will help us to develop our understanding of the MHD as the lecture progresses. And also in upcoming lectures we will have lots of things to explore. So nevertheless, for the time being, we will move on to the first question of this lecture of 10th week. So here's the question. So you have Ampere's law in CGS unit. So 4 pi j plus del E del T equals to C card of B. So if you remember your Ampere's law in magnetostatic case, it is like just card of B, which is around just mu and then J, right? So this is for magnetostatic case, but when we consider the magnetodynamics or electromagnetics, so you will have another parameter which is around del E del T, and there might be another parameter like mu epsilon with this. Okay, so if we consider that in the CGS unit, then the form is like this. Now when we are studying the MHD, what is happening is you have this equation has been written as 4 pi j equals to C curl of B, right? So what we have is this del E del T term has been neglected. So why is this? Because we have considered this del E del T, which is going to 0, right? Now how can we define this, or how can we find out this what are the correct options among these options, right? So another thing is you have E, right, plus if you are in ideal MHD, so E plus P cross B, that will be equals to, let's say, 0. Okay, so now E is essentially minus P cross B, right? So this is your formula. Now if we write it like this one, that 4 pi j is here, so you have 4 pi and then j and then plus del E del T. Instead of E, you can write it del T of, right, minus P cross B, right? And this is equals to C card of B, right? So you have C and then card of B. Okay, sorry. equals to C curl of B, right? Now if we look at this problems, you will find out with this term you will have a V by C term, right? So in this term we will have a term which is having V by C, right? Now if you look at the first question, so you have the plasma velocity in MHD have to be non-relativistic, right? So if V less than C, that means this is less than 1, then we can neglect this term, and eventually we are basically neglecting this daily term, and in that case we are left with this equation. Okay, so this plasma velocity in MHD have to be non-relativistic. This is one of the correct options. So there is no restriction on the plasma velocity, it can be arbitrarily close to C. This is not correct because it has to be non-relativistic. Now look at the third and fourth options. So current densities in the MHD are always divergence free, that is divergence of current density is always 0. Now the question is, you have this J which is curl of B, right? So you have J, right, which is, if you look at CGS, then it will be like 4C by 4 pi, but nevertheless those are constants. So J basically depends upon curl of B. Now if we remember our vector identity, that if you have any vector, let's say B, and if you take the divergence of its curl, so that leads to, if you take divergence of its curl, that leads to 0. So which means your divergence of J is going to be 0, right? So it is basically that this is divergence free, which also means that the current in MHD will not have any source or sinks, because it is divergence free. So that means it cannot diverge or converge anywhere. So it should not have any source or sinks associated with it. Okay, so the C is also a correct option. Okay, now move on to the next question. So before that, what I want to do is just take a screenshot here. I think I can have the slideshow, and now we can have the screenshot, and we can put it on our new slide. Insert. Okay, so let's move on to the next question. Fine. So the next question is, select the correct options. So in ideal MHD, the electric field measured by an observer moving with the fluid is always negligibly small. So see, there are two, like you have this E plus V cross B, right? So this is equals to 0 for ideal MHD, right? So now if we look at this, is okay, so what happens is, this E plus B cross B, this entire thing will give you the electric field which will be measured by an observer moving with the fluid. So it is basically basically this A option is correct one. Okay, so electric field will be negligibly small, but your magnetic field will not have any restriction like that. So the C option is like, in ideal image D, current density can have a source or sink. So as we discussed in the previous question, that in ideal image D, what we have is this divergence of J is going to be 0, right? So if divergence of J is 0, that means it should not have any source or sink. So this A and D, these are two correct options for this question. Okay. The next question here is you have so consider a cubical volume element containing a Z cap directed magnetic field. So the magnetic field is directed in a direction, let's say Z. So select the correct options, right? So if we take let's say, so what we have is in the magnetic field is B equals to, right, B naught and then your Z cap, right? Now so first of all, what is the Lorentz force description is, let's say F equals to the Lorentz force, F equals to J cross B, right? So if we calculate see, B is now B naught is a constant and Z cap is another direction just, right? So now J is defined as curl of B, right? Curl of B. Now if this is like this and there is another mu should be there, mu J equals to curl of B. So if you have this B naught Z cube, that means you should have like J should be your curl of B naught Z cube, right? Now B naught being a constant, so this one should be 0. So your J, which is the current, that is 0. So if J is 0, then J cross B will be eventually 0. So this is also 0 for this question. So there will be no Lorentz force on the volume element, okay? And now the volume element will experience a finite Lorentz force. That's not sure, that's not possible. Now it is not possible to say anything about the Lorentz force on the volume element from the information. Okay, that's not right. And will experience an infinitely large Lorentz force. That's not also a correct answer. So A is your correct answer. And okay. Now if we move on to the next question, so here suppose there is a magnetic field which is this, so By is given by B naught exponential x, right? So your B is given by B naught exponential x, and then it is going in y direction. Okay, so how do we find out whether there is any current density associated with it? That means you have to just do your curl here, right? Curl of B will give you the direction of J. Fine. So if we do this, you will have x, you will have y, you will have z, right? So what to do is, you have del x, you have del y, you have del z, right? And then you have 0 v naught exponential x, and then this is 0. So if we look for this x cap, you will have this one 0, this one 0, so that will not have any option. Now if we go to y cap, this is absolutely 0 here, and there is a minus sign. So, and for z cap, sorry, if you go to y cap, then it will be 0. So if you go to z cap, it will have like only b naught exponential x, and so it is b naught exponential x, right? And that's true for only this one, right? So this is z cap, so which is a non-zero component. Fine. Now if we look to find out the j cross b, what is that? J cross b, that is equals to x, y and z, right? So if we write the j value here, so it will have 0, it will have 0, and then this is b naught, let's say exponential x, okay, and the p is given by 0 b naught exponential x, and this is g. Fine. So if we look to do this, so what you have is, this is 0, this one is 0, sorry, this one is this, so you have a minus b naught square exponential 2x, right? So this one is with x cap. Fine. And then you have y cap, that should have a 0, and then z cap will also have 0. So you see the Lorentz force is in x direction, Lorentz force is in x direction, and this was in z direction, right? And both are not equals to 0. So let us look at the first one by option, one by one, all the options. So it will have a finite current density but 0 Lorentz force. That's not true because both are finite, not non-zero values, right? This one is also a non-zero value. So magnetic tension will be 0 but magnetic pressure will be finite. So how do you think of it? So if we look at the physical implications of different components of a Lorentz force, you will find out this J cross B can be written in two terms. How? So this let's say you have a J cross B, right? J cross B, that will give you curl of B cross B, right? So if you try to find out, you will have two components here. One is magnetic tension, other is magnetic so one should be like B, right, dot grad B, another will depend upon let me, like this can be this B square, and there should be some mu also. So this one is your magnetic pressure, this one is your magnetic tension. Now if we look at this first one, so you will find out that you will have a b naught exponential x, and then you have del del y which is acting upon b. So this one should be 0 for this type of field. Now if we look at this one, so it should have some positive value. This is non-zero, right? So you should have a magnetic tension which will be 0, but magnetic pressure will be finite, non-zero. Okay, so this one is correct answer. Now also another thing you can know that if we try to plot this field lines, what will happen is, let's say you have this one is let's say x and y plane. So obviously field lines are going in the y direction, but as exponential, so as x is increasing, the field lines will field will increase exponentially. So what happens is, if we have here there is a field lines, so if we go higher in x, so it should have like this one, right? So this is b naught exponential x, so it will have like this one. So you should have like, now magnetic field lines are very straight, and along the field lines there is no change in magnetic field strength, so there is no magnetic tension in this case. But obviously you should have a larger magnetic pressure in this area than this one, because here the magnetic fields are more concentrated, so it should have a larger pressure associated with it. So as a result of that, you can have a magnetic pressure magnetic pressure force which will be directed in this direction from higher pressure to the lower pressure. Okay, so that is obviously taken in this also, that this is in the negative x cap direction. So you can find out from the mathematics as well as from your morphological description of the magnetic field lines. So now if we look at the third option, so current density is directed along x direction, so which is not correct because this is in the same direction. So and Lorentz force is directed along y direction, that is also not correct. So also the fourth option is saying that current density is directed along y direction, which is also not correct. So you should have only this second option which is correct for this question. Okay, so fine. If we go to sorry, give me some time. Okay. Now if we look at the next question, so consider a field bx equals to y, by equals to x, and bz equals to 0. So how to find out these things? So current density is finite and both of these. So what we have is the magnetic field here, right? So magnetic field is given by let's say y x cap plus x y cap at plus 0 z cap, right? So your current density will be like J curl of B, right? So how do you find out whether the current density is 0 or not? Again you need to take the curl of it, right? So x y and z, right? Del del x del del y and then del del z, right? So you are in y x and 0. Okay, so if we look at this x cap, you will find out this is 0, then plus y cap, you will find out again this is a 0, right? because delta z of y, that will give you 0, and delta x of y 0, that will give you 0 obviously. So the z cap should have again delta x of x, which is 1, and delta y of y, that is also 0. So this is 0. So your current density is 0, not a finite, right? Now, but it is a force free field. So as you see, your J is obviously 0, so it should not be a current density is finite. So it is a potential field configuration obviously. Now the question is whether the field lines are parabolic or hyperbolic. How do we find out? So this is like you have dy, you have you have dy, you have dx, which will be around by bx, right? So by bx, now by is your x, bx is y, okay? So you have y dy minus x dx, which will be equals to 0, right? Now if we just do the integration of it, y dy minus x dx, that should be equals to c, right? So if we go by this, so we have y square minus x square equals to 2c. So this is not a parabolic curve, right? So this is a hyperbolic curve, which is like this. So how the field lines are going in this? So let us try to draw. So the field lines will be like this one. Okay. This is, sorry, this will not connect. This will not connect. So you have this, and you have this. You have this, right? So if this is going this way, this is going that way. Okay. So this is your field line configuration for this particular case, and it is a potential field configuration because the current itself is 0 here. Okay. So okay, I think that's clear to all of you. Now if we go to the next question, so it is telling that it is a question about the plasma beta. Now how do we define a plasma beta? Is the gas pressure by magnetic pressure. Okay, so just give me some minute here. So you have so you have plasma beta, which is defined as beta equals to your kinetic pressure, which will depend upon the nkt, and then divided by b square by 2 mu, which is a magnetic pressure. Okay, so yeah. So again, you can have like nkt also for pressure. So you can have nkt divided by b square by 2 mu. Okay. So this is the ratio of gas pressure to magnetic pressure. So first one is correct. Now the plasma beta is proportional to cs square by v square, whether this is true or not. Now if we look at CS square, that is your gamma P, right, by rho. And if we look at the B square, which is B square by mu rho. Okay, so this is your answer. Now how do we find out that this pressure term will be what? Pressure term will be rho CS square by gamma, right? And this B square should be BA square mu and then rho. Now if we write down this one, like P is your rho CS square by gamma into 2 mu into 1 by B square, right? So 1 by BA square mu and then rho. Okay, so mu or mu is cancelled out, so rho has been cancelled out, so you should have CS square by BA square. Okay, and there should be another term so which is proportional to this, so the C option is another one which is correct. Okay, I hope you got the answer. Yeah, so sorry, excellent, just give me some minute here. So okay, now what's the next question here is about this one. So for a plasma with Rm greater than 1, now the question is what is Rm. So you know about Reynolds number, right? So here this Rm is magnetic Reynolds number because we are in MHD regime where magnetic field is included. So how do you find out this Rm is, you need to consider the magnetic induction equation, which is del B del T equals to curl of B cross B, right? And then you have eta del square. Okay, so this is your induction equation. Now what is Rm? Rm is basically a ratio between your magnetic advection term and the magnetic diffusion term. Now this first one is your advection term, advection, and this one is your diffusion term. Okay, now what happens, this Rm is given by the ratio between these ones, right? So Vb by L divided by eta B by L square, right? BL by eta So magnetic diffusion is important. So if Rm is greater than 1, that means your PL by eta is greater than 1, right? So magnetic diffusion depends upon this eta term. So if it is greater than 1, so that means you have PL which is greater than 1, that means your magnetic diffusion is not important. It can be negligible. Okay. Now the magnetic flux will not be conserved. So what does advection means actually? So advection means is this is a theorem like Alpin's flux principle. What does it tell? Is if your plasma is moving, so it will drag the magnetic field which is embedded with it, such that at every point in its motion, the magnetic flux associated with that particular plasma will remain conserved. So that means if somewhere your magnetic field lines are very much concentrated with each other, so that means your area in which your plasma is going will be very much contracted. So that means here your magnetic field will increase and your the area will decrease, right? So in that case, so magnetic flux will be conserved, in which condition your advection term is important. So second one is also a not correct answer. So plasma can move freely along magnetic field lines. So obviously if magnetic field and plasma both are coupled with each other, so in which direction the magnetic field lines are going or magnetic field lines are directed, plasma can move freely in that particular direction. So that is one thing. Now the fourth one is in perpendicular direction to the magnetic field lines, so field lines are dragged with the plasma or the field lines push the plasma. So obviously if they have to decoupled, then what happens that if your plasma is moving in a direction which is perpendicular to the field lines, what will happen? Let's say you have, we should have a straight line. Let's say you have this field lines, okay, this one, and if your plasma is moving in this direction, let's say in this direction, so it will continue to move in this particular direction. But when your plasma is basically moving in this perpendicular direction here, so that means what it will take is your magnetic field lines can be like this, right? That means you are dragging your magnetic field lines in a direction which is perpendicular to the initial configuration of the magnetic field, such because of the movement of the plasma in that particular direction, right? So this will be your final configuration due to the advection term itself. Okay. So third or fourth both are correct. Now the next question is, you have again just few minutes earlier I have written the magnetic induction equation in a particular form, which is del V del T equals to curl of V cross B plus eta square square B, right? So I have written like del V del T equals to curl of V cross B plus eta grad square B, right? Now if I neglect this one for the time being, so you will have curl of V cross B, right? Now if we know the vector identity, we can write this form in this particular form, right? Now if you remember this one given in the left hand side, which is del v del t plus v dot grad b, this is basically your material derivative, right? So you will have the change of the magnetic field due to the time, and also the change in the magnetic field due to the spatial position along the flow, right? So this will entirely give you the total change in the magnetic field in terms of spatial change as well as the temporal change, right? And that total change will depend upon two parameters here. First one is this one, second one is this one. So if we look at this one, so it will tell the change in the velocity in the direction of the magnetic field itself, right? So now look at the first two options. So according to the first term on RHS, an accelerated motion along field causes the field strength to decrease. Now this is coming with a positive sign. Now if the grad of V is greater than 0, right, along the magnetic field line, so this is a positive, right? So this is a positive. So if it is a positive and also this is with a positive sign, so that means it will give you the increment in the magnetic field strength, right? So this is your correct answer. Okay. Now the second thing is, now according to the second term on RHS, which is basically your divergence of V, that means the velocity's divergence, and which is multiplied by the magnetic field itself. Now an expansion and compression can cause the field to decrease and increase respectively. Let us look at like what is card of P, right? Now if we remember our del rho del t, right, plus what, divergence of what, rho p, that is equals to 0 from mass continuity equation. Now you should have like del rho del t plus what, rho divergence of V, right? Another is V dot grad rho, this one should be 0. So if we look at this first and third term, that will give you the material or total derivative, right? D rho dt, right? And along with this you have rho and then divergence of P, right, which is equals to 0. So now what it suggests is, let's say you have gradient of V which is greater than 0, that means your this term is positive, right? So if it is positive, then del rho del t, sorry, d rho dt will have to be negative, right? So if it is negative, that means your density is decreasing with time. So density decreasing with time means it is an expansion, right? So this is an expansion. Now for expansion, you have divergence of P which is greater than 0. So if your divergence of V is 0, that means this term will be a negative term, right? So if it is negative, then your magnetic field should decrease, right? So an expansion causes the field to decrease and compression causes the field to increase respectively. So this third one is a correct answer, because you can derive the vice versa from this discussion. Okay. So let us look at the next question here. So choose the correct option. So for a given boundary condition, a potential magnetic field configuration has the highest energy. So among all possible configurations that satisfy the boundary condition, which is not correct. So for a potential field magnetic field configuration, what happens is it should have the lowest energy configuration. That means it is the equilibrium magnetic energy configuration. So if somehow a field has been perturbed with some energy, so it will try to regain the potential magnetic configuration by losing its excess energy by some other means, like by transporting it to other layers, or by let's say explosion of some materials, right? So it should have a lowest energy. Okay, so this is P. Now for a given boundary condition, if the magnetic field is in non-potential configuration, it will tend to relax and finally attain a potential configuration. Okay, so what I was suggesting, so C is correct. Fine. So okay, so this one has to be correct. Okay, so I can just new slide, insert. So that's all for today. I think you will get benefited from this questions, and you will have some better ideas about what are the questions you may prepare when you go to some Viva or some exam. It's only 9 or 10 MCQs, but most of the topics from basic MHTs except the energy equation has been covered in this MCQs. So you have the understanding of the flux bridging condition when the advection equation is dominant over the magnetic diffusion. You know that due to flux bridging, what happens is magnetic field and the plasma are coupled with each other. So if plasma is moving in a direction which is not in exact parallel direction of the magnetic field, then magnetic fields are also get distorted by the motion of the plasma, and vice versa. Let's say magnetic field is moving in some direction due to some region, then it can interact plasma with it also because of the conservation of magnetic flux. And again we can define the Reynolds number, which is a ratio of the gas pressure and the magnetic pressure, and depending upon that we can have the ideal MHD and resistive MHD. So if we have Reynolds number which is greater than, sorry, it's not a, I just forgot, this is not gas pressure by magnetic pressure, this is basically a ratio of the magnetic advection and magnetic diffusion. So if Reynolds number is greater than 1, that means your advection term is important, and the flux bridging is there. And if this is less than 1, then we are in the regime in which we are considering the resistive MHD, and then we can have the magnetic recognition, which we will be discussing in some other some later classes. So these are those things. Now with these basic things in MHD, we may be in a position in which you can study about the different kind of MHD waves. Now when we are considering only the hydrodynamics, we have been considering, or we have been talking about the sound waves only, but now we have magnetic field, and introduction of magnetic field along with the plasma itself, it will gives rise to major different two or three major different wave modes, except only the pure acoustic mode. So now we will consider, yeah, so that we can discuss in the later class. So also we have a discussion of the plasma beta, which is basically a ratio of the gas pressure by magnetic pressure. So if we consider the solar atmosphere, why I'm telling about the solar atmosphere, because sun is a very natural laboratory to study all the plasma processes. So if we consider the solar atmosphere, you can find out that if we go to the photospheric region, so you will have the beta will be pretty much higher than 1, because that means your gas pressure is dominating over your magnetic pressure. And if we go to the higher in the atmosphere, in the corona, you will find out the beta is lesser than 1. That means your magnetic fields are dominating your plasma processes. Okay, so these much things have been acquired in today's class. So we'll come back with some description of the magnitude of a different type of wave modes in a, in a in a plasma which is having some associated magnetic fields with it, right? So yeah, okay, so for now we can stop to this class or student discussion. Hope you guys got will be benefited with this class. And so thank you very much. We will meet on the next Saturday again at this time.